to share the screen. Okay, so let me know if my screen is visible. Okay, is my screen visible?
Yes, ma'am, it's visible.
Yes, ma'am.
Okay, so today we will start with distance-based classification for product recommendation, and we will learn about the K nearest neighbor classification. So we all visit the e-commerce website these days, right? And many a times we do not search with say a specifically do we say that I only want to take a specific type of dress or a specific type of gadgets. No, right? We give a generic search like cotton kurta or Bluetooth headphones, and the e-commerce websites return us various results, and when we click on one of the results that we find interesting, the page also shows us the similar products, right? So these similar products are an important part because we many a times the customers who are visiting the e-commerce website will also go purchase from those or purchase from the recommendation. So the similar products recommendations in any retail websites are an important component. So how do we do that? How do we identify which are similar products? So when we search a product, retail websites suggest similar products, but how does it know which products are similar to the original products? And also what is meant by similarity of products? How do we say that this product is similar to this product? Because it does not say that similar, but it says that but you may also like these products, or customers who have purchased this have also looked into these products. That means similarity is not only like how the two product looks or the type, or whether the products also go together. So one such notion of similarity can be based on the customer statistics. So one thing, if at any point of time my voice is broken or the connection is unstable, or you are not able to hear me properly, please let me know. And also if you have a question or query, please feel free to unmute and ask it. But at all the other times, please keep your microphones and the video stand off. So the one notion of similarity can be based on the customer statistics, just like I said that many a times it is shown that customers who have purchased this product have also looked into these other products. And another notion of similarity can be based on the feature of product. Like say if I am looking for some Bluetooth headphones and I am browsing for the headphone of a particular company, the other similar headphones like in the similar price range or similar attributes, it pops up. So recommendation based on statistics, we all know it looks like this. So if someone is looking for a DSLR camera, then frequently brought together items, we often see that you can take a lens, and there is like these three items. If you purchase them together, there will be certain discounts because these are frequently brought together. So these are the accessories. Or like not exactly. So a lens is not exactly a camera, but as these two are brought together, so they may consider similar to each other. There can be some recommendation based on features. Like often if we go for purchasing a shirt, some tie recommendations come together, that because people have bought them together. But are they similar? Not in the features, like in the strictest of terms, in the feature space, they are not, right? But what we also do that when we are say we just go and share something like black t-shirt with a graffiti. Okay, so there can be also the similarity based on the same types of products. So like the in the product type matching, the recommendation system should show other charts. Like if I select this one, say I want something like this. This is in my mind. So I type that black shirt with some the writings and particular types of the images, and say on from all the browse listed items, I click on this. So what my recommendation system should also do, that it should also show different types of chart which are similar to it in the viewing. So the similarity can be defined in terms of attributes like color. If I am looking for black t-shirt, then it is black. Some people may have fondness for some particular brands or some texture like cotton or mixed or polyester, or perhaps even the design, that whether to have a collared t-shirt or not. So these are some of the example that how exact, like in the ideal terms, how the similarity should be grouped. So if this is the items that I am interested in or I am browsing, this is a positive similarity match because it is a black t-shirt, full length, and it has similar types of prints on the t-shirt. This is a black full sleeve t-shirt, but it is not a similar item because and we call it in class negative because it matches these attributes, the colors, the size, the texture maybe, but not this logo. This is not one thing. And this is out of class negative because in this case we are not matching any of any of the product features are not being matched. Only this writing is matched, but this may not be the most important uh, feature. Uh, Maybe my primary thing is that I want a black t-shirt. So now when we talk about similarity representation, so in machine learning terms, how do we calculate similarity between two products, or products means two data points, right? So we have all read about the features in the earlier classes, if I am right. So what we do, we represent each product by a vector of attributes or features. So now each product will be a feature vector X, and the ith product or the data is denoted as Xi. So in my training data set or in the known data set, annotated data set, I have the Xi and Yi, right? For each of the feature vector corresponding to each data point, I have a label. Okay. So what I need to do, what is the output that I need, is that given a new data point that is X test based on its feature vector, what will be its label? So the label is to be predicted. So this is a supervised learning. So this label, as we know, they can be binary like 0 or 1, like in class or out class, positive or negative. They can be discrete class labels if there are multiple classes, or they can be continuous values. Say, for example, that I have a set of set of heights and weights of a particular group of people, and so this is a continuous label space, right? Because there is no discrete weight labels or discrete classes in the label space. So binary label, like uh, product recommendation, as we are seeing, similar or not. Discrete label can be rating by the one user, like 1 star, 2 star, 3 star. So we can see that in the retail website, being it e-commerce or even the travel website, there are options that we can sort by the different stars, like 4 stars or more. When you order from Zomato or Swiggy, we often sort using this manner. And the continuous levels are the mean rating by many users. Say for example, I have asked the user to say a number of users to group to rate a particular item in a scale of 1 to 5. Now, instead of taking the mode that what is the most frequently occurred rating, which is generally done, I decide that I will take a mean. So if you go to a travel website like booking.com, so there you will see the values are not in actually 1, 2, 3, 4, 5. It comes like something like 7.6 or the 8.3. So these are the continuous levels, because um, so there can be, you know, 10, so from 1 to 10, uh, 10 labels, and for each I can again have like this 1 to 10. So anyone from the 100 values. So how can we, if we are going for the classification problem, say the discrete label space, so what can be a simple idea? We have the training data set of xi, yi, where x is the feature vector and y is the label. Just a moment. And we have the test data. That x test, that is the new item or new data point, and we have to predict its level. And x is here representation of the data points or the features. So the features, as we have described, can be the type of material, can be the price range, even it can be the color, it can be brand, it can be its size. Okay. So our idea in the k nearest neighbor, we have all heard the term like the birds of flock fly together. So the same idea, that but that if things that are looking similar, then they are usually of the same type. So this is the idea behind the k nearest neighbor, that we try to identify which training data points are similar to the test data point, and we we assume or we predict that then the test data point will have the uh, same label as the similar looking training data point. So if x test is equal to xi, then probably the y test will also be equal to xi. So if my test data points look similar, or in this case actually equivalent to my ith training data point, then the label of my test data point will be most probably also the label of the ith data point. Now the question is that how the thing that we are saying, that birds of feather fly together, that the similar birds, they always fly together, and similar data points, they will have the same type or they will belong to the same group. So how do we define this similarity? But before that, there are some other questions also to address. That first of all, is x is a good enough representation? Because x is nothing but a feature vector of my data point. So how do I choose the features? How important they are? I think you have also read about the importance of different features, the information gain, uh, uh, to be considered while choosing different features. So is X is a good enough representation? Because uh, how we define X, that matters. And also in reality, this assumption that my test data point will match one of my training data point will rarely happen, especially if X is a continuous variable. Then the probability is very, very rare, right, to actually match the test data point uh, to a training data point. But let us assume it is. Let us assume that X is a good enough representation. So we are not going to the how we come up with the feature representation, but we are assuming that we have a good feature representation, and then how do we calculate the similarity? So how do we calculate the difference between the feature vectors? Because that's how we will measure the similarity. The lesser the distance, the more similar two data points are. Now, if x is a continuous, if x is continuous value, then x case, that is the text data point matching one of the like I training data point will almost never purely happen. But what can we assume? That it is a close match to the ith data point. So my test vector, test feature vector is very closely matched to my ith training feature vector. Now, what does it mean, like this close match? It means that generally the distance between these 2 points are very less. So when we talk about distance, we generally consider the Euclidean distance between the 2 data points, and this is represented by this, that mode of x test minus xi is very low. Okay, this 2 is because this is the L2 dot, we will come there. So how do we calculate Euclidean distance between 2 data points? So if say one data point, now forget about this complex feature vectors, let us go back to our basic geometry. So, okay, I do not have any drawing tools here. Just give me a moment. Let me see if you have. Okay, so sorry, I need to check it. I not able to find it. Anyway, so sorry for the interruption. So how do we calculate the Euclidean distance between two data points? That in our geometry we learned long back in school that if a point is represented by say the x1, y1, and another point is x2, y2, then the Euclidean distance between two of them is the root over of x2 minus x1 square plus y2 minus y1 square, right? That is the distance between 2 points on a two-dimensional Euclidean space. So in this case also, say if A is my one data point and A contains like n number of features, and B is my another data point and B contains n number of features, then how do we calculate the Euclidean distance between these 2 points or the 2 feature vectors if there are n features? So for from I equals to 1 to n, each ai minus bi square summation of those and root over the whole. So like we used to do from two-dimensional to three-dimensional, the logic remains the same, but instead of only x and y, in 3D we also used to have the z variable. So now one other term will be like x2 minus x1 square plus y2 minus y1 square plus z2 minus z1 square and root over on all of them. So in this way, we calculate the Euclidean distance also here in between the two feature vectors. And this is also called the L2 norm of A and B. Okay. So what do we do in the nearest neighbor classification? So we have n labeled example, this xi, yi, where I equals to 1 to n. So the function learned is the training set itself. And then testing is the X test. We have a new data point and we have to learn the prediction. So how do we learn the prediction? The y plate, that is the label for the data point, will be the yn or yi, where this small n is equals to minimum of the x test minus xi, that is the L2 norm or the Euclidean distance, as we have just seen. The Euclidean distance between the x test and all the n data points, for which one the distance will be lesser, we will take the argument of that. Here argument means the label of that. Or to put it in the simpler terms, that we compute the Euclidean distance between the test data point and each of the n training data points. Say we have 100 training data points and we have a new test data point. So we compute the distance between these training data points and all the 100, distance between this test data point and all the 100 training data points. Then what we choose, we sort the distances from mean to max and we see which one training data point has the minimum distance with the test data point. So that is my nearest neighbor, right? So that's how the name has come. That which training data point lies closest to the test data point. And we assume that as it is the closest, then the prediction, so the label of my training data point will also be the label of my test data point. So we use its label as the predicted label of the test point, because the similar looking items are grouped together. They also lies very close to each other in the feature space. That is our assumption, right? Now there are certain concerns, because our entire calculation is dependent actually on just like entire prediction is dependent only on the one training example on whose distance is minimum. So it is not very robust to outliers, right? Because if the closest training point, which will is an outlier, then my predicted label will also be wrong, because it will take the label of the outlier and it requires a lot of computations, because each n with each training example, the distance with the test data point needs to be calculated, and also they need to be stored and they need to be shorted. So there are computation for distance calculation and computation for this shorting. So let's see an example. So this is, can you see the screen, the picture?
Yes, ma'am.
Yes.
Yes, ma'am.
Okay. So the so this is the picture of the K nearest neighbor classification from the Wikipedia. So if you can see, so generally our assumption that the closest training example will be the same label as of my test data point is actually based on something like this, that all the similar classes, the items or the training data points in the similar classes will be grouped together in this, like in the distinct groups or distinct clusters. But what happens that we know that it is not always the case. You have read about the maximum margin classifier, so you also know that it is not always that in the class boundaries, along the class boundaries, the different the members of the classes are exactly on the other sides of each other, right? So now take an example in this case. Say if I have my test data point, say here where my arrow is. Now what will happen? As you can see that my test data point is actually in the red region, but my classifier does not know red, green, blue, right? But when I compute the minimum distance, the problem will be that actually the minimum or the nearest neighbor to my test data point is this green data, not the red ones, right? So in this case, my classifier will wrongly predict that the label of my test data point is from the green class and not from the red class, because it is taking the label of the outliers. So this is a problem when we depended on only the one class. So how do we um, alleviate the problem that the nearest neighbor of the test point may be the outlier? So there are two things. First of all, outliers are rare. That is why they are called the outliers, because they do not follow the other regular trend in the dataset. And instead of just one nearest neighbor, if we take k nearest neighbor, so instead of just computing that only my label of my test data will be predicted based only on the nearest training data point, if I say it will be predicted based on my k nearest training data points. That will, I will not take the attributes of my immediate next door neighbors, but I will learn from like my next door neighbors, my opposite neighbors, my next building neighbors. So this kind of thing. I will try to come up with an average attribute or average data point. And if I take the k nearest neighbor, so it is very unlikely that all the k's will be the outliers, right? If we go back to this picture, if instead of just one neighbor, if this is my test data point where my arrow is, as you can see, if I take k, then all the others are actually the red data points, right? So then the chances of getting the label of the outliers also reduces. So what is my solution? So I will repeat this first step, that I will compute the Euclidean distance between the test data point and each of the training data point. But now I will sort the training points according to the distance from the test point. And I will choose the first k training point which have the minimum distances. And then we predict our label as the most frequent label among them. So the k data points may have different labels, but we will take what is the most common occurring and we will. So for regression, it will be the mean of the label, and for classification, it will be the mode of the labels. Because as you, I think you have also covered the ensemble classification. So there also we are doing the same thing, that if it's a regression, then from all the classified output we take the mean, and if it is the classification, then we take the mode. Now there are some other concerns as well. So how do we choose k? So if from this picture, that we can see that if we choose k as 1, then the chances that we are picking up a wrong label because my nearest training data point is an outlier is very high in most of the cases. We saw that if we take k as a large value, okay, how large? Say if we take k like kind of, 10, 15, then what happens? Up to say like 5 or 7, I am getting all the button, except for the one, all the nearest neighbor in the red region. But if we increase k too much, then say for example, some from this green region will also come, some from this blue region will also come. So if we expand my number of nearest neighbors to a lot, if the k becomes very high, then actually up to a point we get a more accurate prediction. But after that, actually we start to get more errors or more noise. Because just think that if you increase your neighborhood, if you consider your neighborhood to have a large diameter, then the variations or then the differences in this place, the class levels, that will also be too high to come up as an accurate prediction by using mode or mean. So what we do, we generally keep k at an odd value, so that in case of mode calculation we have some tiebreakers. So generally it is kept at something like 3, 5 or 7. Like that. But in this k nearest neighbor, there are still my problem of the computation and the storage requirement is persist. Okay, because how many computation I need to do? Still n, because I need to calculate all the n distances, and then I also need to store, like d is my dimension, so this much n into d plus n storage is required. N storage is for the n distances and n d is for the n data points. Okay, d dimensional data points, and this is also only for the distance calculation, and not even for the sorting problem that we need to address if we need to sort the data points. So now what can be my solution? So one of the proposed solution is called the nearest mean classification. So now again the idea is that, say if I am assuming my the examples in the training set belonging to different classes, they are grouped in different clusters, right? So then instead of taking all examples belonging to the same class, can we just come up with one of the representative examples like we do in class, right? In different classes, what do we say? That elect your class representative, and it is likely we assume that the class representative will represent the attributes or expectations or frustrations of each members of the class, right? So the same assumption also goes here. Especially if we assume that the clusters are spherical or nearly spherical, then actually the mean is a pretty good representation for the class. So what do we do? Instead of considering all the training data points belonging to one class, we come up with one class representative. So generally the class representative is calculated as the mean of feature vectors of the all the data points in the class. Okay. So that means uh, uh, that I take all my training data points belonging to belonging to one class, and I just add value of all the different features in the feature vectors, and I take an average of that by dividing by the number of samples. So say for example, the mean for my class K, mu K is represented by this. So I take the sum of all the features of the training data points. This sum is for I, like if I have say like D features, so sum over D, for which the class level is K, and I divide by again the number of the data points for whom the class level is K. So now instead of calculating the distance of X test with all the training examples, that is the n training examples, I only calculate with the representative of each class. So only with each mu k, and choose the level of the closest. So again, as you can see in this case, we are not doing k nearest neighbor, but we are taking the mean of the class and doing the one nearest neighbor, that is only the closest nearest neighbor. So my y prediction will be our mean of x test minus the UK, the which is called the L2 norm of x test and mu k, or the Euclidean distance between the x test and the mu k. So in this case, instead of n, we only need k comparison. And now, as you can understand, the number of data points can be in like order of hundreds and thousands, but number of classes will be what? In order of tens. So and this is just a summation operation, right? So now my number of comparisons are very less, or the number of computations are also very less. Uh, and the other point is this till now we have used Euclidean distances for calculating the similarity between two data points, but there are also other distances available which may like depending on the multivariate feature space. The one most frequently used distance matrix is called the Mahalanobis distance matrix, which is also called the metric distance. So we can also like modify while calculating with the while calculating the nearest neighbor. Instead of the Euclidean distance, we can also use other types of distances based on our vector feature space and our applications. So, okay. So as you can see, this k nearest neighbor has the advantages that we are like, but we are only taking the training data points, and there is no other new function to be learned. So we are only comparing the distance with the test and the training example, and we are taking the label of the closest training example, or by mean or mode of them. Uh, but it also has the disadvantages that it requires large number of computations, and sometimes it is not very robust to the outliers. So this is in the use in many of the practical applications, like the e-commerce, for search and retrievals, for product matching, this kind of things. And just remember one point. So this gets confused most often, that k nearest neighbor is actually a supervised classification. It is a non-parametric supervised classification. Okay, it is not unsupervised classification, or not unsupervised the learning. Sorry, I should not use the term classification, but learning. Okay, so any question? Hello, any question till now?
Ma'am, can you explain the formula you use for finding the
Yeah.
previous slide?
Can you speak up a bit? I am not able to hear you. Shreya?
Can you explain that formula you used for finding the mean of all the features in the previous slide?
Okay. So for this one, right?
Yes.
Yes. So basically so what we are doing actually is that we are taking all the training data points which has the class label k. So this is a 0, 1 function. That means if y equals to k, then this value is 1. So we will take this particular training example, and if y is not is equal to k, then it will become 0, and that particular training example will not be considered. Okay. So in the simplified terms, we are taking, say for like class rate, there are 10 training data points. So we are taking these 10 training data points, and for simplicity, just assume that each training data point is represented by only two features, feature both y and z. Okay. So what we are doing, for all the 10 examples, we are adding the 10y features, and we are adding the 10z features. Then we will get not a new vector, right? Am I correct?
Yes.
So this is my sum of the feature vectors. And now how I will do the mean of the features vectors? I will divide it by the number of the training data points in the class red, which we took as 10. So these summed feature vectors will be now divided by 10, and again the result will be in the form of this y plus z only, right? So this will be the mean feature vector for the class red. So was I able to explain?
Yes.
Yes.
Yes. I got
Yes. Anyone else? Anyone else have any question? Okay, then I will just stop the screen share for a moment uh, to change the slide. Okay, so okay, let me know if you can see my screen.
Yes, ma'am, we can see.
Yes, ma'am, we can see.
Okay. So with the k-nearest neighbor classification, we almost completed the supervised learning part of our course. Now we will go to the unsupervised learning. So in the unsupervised learning, we will first learn about the graph clustering. So about graphs and graphs clustering. How do we do unsupervised learning on graphs? So before we start, as you can recall that in supervised learning, how do we learn? That we take help of the annotated training data set. So we have a annotated set in which we have some training examples and their class levels or their values, and from training a classifier or training a function on the training dataset, we learn a model and that we use to predict a new test data point. So in the unsupervised learning, as the name suggests, that we do not have many annotated to training data. So it is almost little or no annotated data set that we have. So we do not know we do not know for a set of data the class levels beforehand. So in the graph clustering, we will learn three things: minimum card, hierarchical clustering, and spectral clustering. So let's see how much we can do in today's class, and tomorrow we will continue this. So clustering graph, or network data. So graph means graph is actually the networks that we see in our real life or in practice. So if you think in the mathematical terms, they are graphs, right? So far we have talked about data as n-dimensional point. As we have seen in our last k-nearest neighbor classification, that we are taking our training example as a feature vector over say d-dimensional or an n-dimensional feature space. But and also no two training examples were kind of connected to each other. All of them were treated as the discrete examples, right? But what about the following things? Say we have the Facebook friendship network. So if we go to Facebook, it recommends us, right? So these may be a potential person whom you can send friend request to. So that's how we grow our network, correct? So that means Facebook needs to have some mechanism uh, by which they can say that okay, this if this is the network of this person, then the next addition to the network may be this person. In the community question answering website like Quora, so the question answering itself is an NLP problem. But here, how do you know that those of you who are subscribed to Quora, you can see that it sends you recommendations that okay, this question may be interesting to you or useful to you, and it also suggests you that some of the communities that you can subscribe to or the question you can give answer to. That means it has to have a way to connect different data points, right? Or say those who you are interested in say like biochemistry or medical some machine learning for biomedical purposes. So as you know that one of the dominant problems these days is to actually computationally simulate the drug-drug interaction, the protein-protein interaction to come up with new stable drugs, right? Before we actually go into the experimentation phase. So how do we do that? So this is my friendship friendbook, Facebook friendship graph network. So what do I want to do? Say what does Facebook do? Or even when we mix, like you say na that my these are the different groups of friends that we have, but I like this group more than this. So how do we come up with the terms that groups? How do we come up with the terms that in a friendship network, some people are connected more closely together than the others? So basically the problems that we address every day is to find coherent groups or find friend circles, whether it is in Facebook or it is in the real life. So to find coherent groups, just give me a moment. Yes. So what do we need to do? Again, the same thing, group similar objects. But only in this case, we do not have any information about the groups or the classes or the clusters in beforehand. So our whole objective is to learn the group. So essentially, it is again a grouping problem with different type of data. This is another example of the protein-protein interaction network. So as you can see, some types of protein interacts with each other or can be grouped together than the other types of protein based on their interactions with other proteins. So there are some, as you can see, take this green cluster. As you can see, this member interacts with this yellow cluster. But why have we colored it green and this one yellow? Because these many, they have large interaction, like a lot of interactions among themselves and very lesser interaction with the outside people. So this is the interaction cluster. Okay, they can be grouped together. So all these groupings that we use in our chemistry, use in our biology. So all these are founded on the similar kind of assumption. Like, what do you say group? Do we say group? It is not that one member of a particular group does not interact at all with the other member. But if some members they interact a lot with each other, a lot more than they interact with the one of the outside, then we say the groups. Now, when we do machine learning, my computer does not have any idea that okay, this is a green cluster, this is a yellow cluster, this is a pink cluster. It only has these the interactions. So now our job is to come up with a function that based on this frequency of interaction or type of interaction or the weights of the interaction, we can tell okay, cluster this. Okay, this is a group, this is a group. This is the in group interaction, this is outside group interaction. So for that, we first need to understand what is a graph. So a graph is composed of two things. First of all, it is a set of objects called the nodes of the graph. So like these individual people in the friendship network, so these are the nodes of the graphs. And these two nodes are connected to each other via an edge or a line or some connection that is called the edge of the graph. So the sets of connection. So this is a node and these are edges. And there are different types of graphs, like the unweighted graphs or weighted graphs. If you recall your basic graph theory or mathematics, you have learned about them. So in this graph, the edges do not have weight, or we can say that all the edges have similar kinds of importance. So here only the one thing that matters, that whether two nodes are connected to each other or not. Like the A and C are, but E and I are not. There is another type of graph that is called the weighted graph. So where the edges have weight. The weight means some the edges may have more importance than others. Like in the email communication network, say A and C are two persons, and A and C communicate lot more often than the A and E. So in both cases, there is a connection with A. C is also connected, the E is also connected. But let's assume this AC edge has weight 6 and this AE weight has H1. That means AC communication channel is more important or more frequently used or more interaction is happening than AE. Or the city or road network, here what also we can capture is the distance between the two cities. Say for example, Calcutta and Delhi is connected by national highway, and Calcutta and Chennai is also connected by national highway. But the distance may differ. And when we come up with the city road network, we may want to assign different weight to these different connected networks. Because this weight will down the line, say if I want to do a resource allocation, or if I want to transport a particular thing via these networks and I want to go to the path of minimum weight. So in this case, minimum weight also means minimum distance. So that's how the optimization problems are solved. There are also other two types of graphs. All these are, as you can see, these are the undirected graphs. That means the edges, they do not have any direction. So we can go from say like A to C or C to A. But in many of the practical applications, we have something called the directed graphs. That means the edges have direction. Say example, I can only go from B to I, but I cannot come back from I to B. So these directed graphs. So we will discuss about them when we come to their applications. So graph data shows relationship between object pairs, that is two objects. So therefore the centroid, like we were calculating the mean mode, these are all measures of the central tendency, right? Statistically. So they are often not valid in the graph. Because what does centroid mean in your Facebook friend network? You just cannot average and say, okay, this person is the representative of my network. No. Then how do we define? But in many of the mathematical operations or machine learning operation, we need to identify a center. or so how do I define that? So we will stop to this class here. So I hope you have enjoyed. There any question till now?